Hey guys, today we're going to be talking about vector components. Whoop whoop, vector components. So we've already talked about finding the resultant of two vectors, which means adding them together. Adding vectors together. But now we're going to talk about components. And components, finding the components of a vector means taking a vector apart or splitting it into parts. Taking a vector apart or splitting it into parts. So when you're looking at this picture here, imagine this is a nice little red wagon that is being pulled by a kid. We're going to use vector components a lot, especially with forces and things, which we're not getting into right now, but this is a force. So here's a force. There's someone who is pulling this little red wagon. It's super fun. They're loving their life. And you can see how they're pulling this wagon, and they're not just pulling this wagon sideways. They're pulling it sideways a little bit, but they're also pulling it up a little bit. Do you see how that's true? There's a little bit that's going sideways here. They're pulling it kind of sideways, but they're also pulling it up at the same time. It's the same thing if you had a lawnmower. Here's our lawnmower. And you were pushing, wait, I'm gonna do that better. That doesn't need to be that thick, guys. Okay, so here's my lawnmower, and here's my handle, and I'm pushing, you see how I'm pushing down on this handle, but I'm also pushing the lawnmower forward. So you can already start to see this is all that components is. It's breaking down one vector into its different up and down parts. That's pretty much it. So when in physics, and also in math, but especially in physics, we use x and y to talk about the up and the down parts of a vector. So if we have a vector like this, we set our axes. Always set your axes. That's like a good thing for always. Always decide what your axis is going to be. So here's our positive x direction. That's our sideways direction. Here's our positive y direction. So for this arrow, we have some amount of it that's going in the x direction. It looks like it's about this much going in the x direction. And we have some amount of it that's going in the up direction. Do you see how this is being pulled sideways and also up? So we can break these down into its parts. This is the y part of the vector, and this is the x part of the vector. The way to make sure that you do this right is that whenever you're breaking a vector down into its parts, you should always have a right angle between your x part and your y part. You should always have a right angle there. They should always be perfectly perpendicular to each other because that's how our axes are defined. So one thing that's helpful if you want to look at it this way, let's look at this next one. If you want to look at it this way, if you want to draw your axes really, really big, look, here's my, whoa, I want this to be a little bit straighter. Okay, so here's my graph. Here are my axes. This is my positive x direction. This is my positive y direction. So if I'm imagining this is on a graph and our tail starts at 0, 0, then I can see how far did I go in the x direction. I went about this much in the x direction, and then how far did I go in the y direction? And I went down about that much in the y direction. And you can see that right here in between them is a right angle. So let's do one more. I want you guys to try to do this one by yourself, but try to separate this into components. That's all we're doing today. We're just taking one vector and we're separating it into its x parts and its y parts. So go ahead and try that one on your own. Okay, so for this one, I separate it into the x and the y. So this is my positive x direction. This is my positive y direction. And then I'm going to draw things that are parallel to these lines. So here is my x component. I know it's, well, that was a bad line. I'm dissatisfied with that line. Okay, that's a little bit better. Here's my x component. I know it's my x component because see how it's going in the x direction? It's like perfectly parallel to this line right here. So this is my x component right here. I always put the arrows, by the way, in the direction that the arrow is. So I put an arrow right here because it's going from here. This one is going horizontally from here to here. So there's my X direction. My Y direction is going to be down like this. Down like this. So this right here is my Y, and this right here is my X. Not to make anything way too super complicated, but you can see how if I knew an angle, like let's say I knew this angle right here, if I knew this angle theta, I could use trigonometry to find out what X and Y actually are based on what the length of this one is, on the length of what this one is. So this, we'll call this R. The reason why I'm calling it R is because it's our resultant. If we added up X and Y, if we added up those vectors, just like we've been learning to add up vectors using the Pythagorean theorem, then we would get this R. This would be our resultant. So again, components is just undoing adding vectors together. It's taking them apart. So if you added X and Y together, you would get this R resultant. If you took R apart, you would take it apart into the X part and into the Y part and into the X part. So here's our resultant right here. If I knew what this R was and I knew this theta, I could find out what X is using basic trigonometry. So if this is our theta and I want to know what X is, I can do opposite, because it's opposite angle theta, over our hypotenuse. So opposite over hypotenuse is where we use sine. So sine of theta equals opposite over hypotenuse. We can solve for X here by multiplying both sides by R. And this is what would be our X. So we could find out actually numerically whatever X is. And we could do the same thing for Y. So for Y here, Y is the adjacent to theta, and we know R. So if we have adjacent and hypotenuse, we use cosine. So cosine of theta equals adjacent over hypotenuse. We can get Y by itself by multiplying both sides by R. So then we get Y equals R cosine of theta. So that's how you can find what those are. Also, you know that if you use Pythagorean theorem, because this is what we've been doing. We've been doing this the whole time. We've been adding vectors. You can do x squared plus y squared will give you r squared. So you can see how you could really easily go between these things. We'll do some practice with it for sure, and you're going to do a lot of practice with breaking up different vectors into their components. But now let's look at this picture right here, and we're going to imagine for a second an object that follows this path. So maybe we have a ball right here, and it starts here, and then it goes goes all the way up, and then all the way back down, like that. So maybe someone throws it, and it makes this kind of parabola shape. So we could see what the velocity vectors would be like this whole time. So first, it'd be going, let's say someone throws it, so it's going up pretty fast, like this, and then it's still going up, but my arrows are getting shorter and shorter. Why are my arrows getting shorter and shorter? Because that shows the magnitude of the velocity, and I'm getting slower and slower and slower as I get towards the top. Then, on my way down, I'll speed back up. So I'm getting faster and faster and faster. Technically, actually, if I did this right, then my first arrow should be the same length as my last arrow, because it's going to go fast, slow, slower, 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 slowest right here, slowest, and then it will start getting fast again as it comes back down, and it'll be just as fast when it comes back down as it was when it left. So if we had something like this, now we have a bunch of vectors. If we had an x direction and a y direction, we could break all of these vectors up into their components. So let's take a look at we'll just take a look at this one right here. In the x direction, it's going about this far in the x direction, but then in the y direction, it's going about this far. And then over here, you would have something that's going about this far in the X direction and this fast in the Y direction. So you could see we could do this for the whole time, something that's going this fast in the X direction and then this fast in the Y direction. And then you could have something that's going this fast in the X direction and this fast in the Y direction. So you could see how we could break that all up into components. And this right here, my good friends, this is projectile motion. Projectile motion. Wow. So we are going to be looking at projectile motion. In class, we're going to go into this more in depth. But here's the secret that I'm going to tell you right now. I'm telling you the secret right now. But we're going to talk about it in class because it's going to make sense and it's going to blow your minds. Basically, in projectile motion, the length of this green arrow of your X direction will always stay the same in projectile motion. It will always be like this. It will always be, and it will always be the same length the whole time. And the length of your Y component will be changing the whole time. So it'll be getting shorter and shorter and shorter and shorter as you go towards the top, and then longer and longer and longer as you go back down. So we are going to talk about that a lot more, but that's kind of just like an intro, getting your feet wet into projectile motion and breaking it down into vectors. So that's vector components, guys. Way to go.